So welcome everyone to today's webinar. It's my great pleasure to introduce today's speaker, Karmel Shehadeh. Karmel is an assistant professor at Lehigh University. She got her postdoc, she did a postdoc before this appointment at Carnegie Mellon University. And before that, she obtained her PhD at the University of Michigan. Her research lies in the interface of a stochastic and robust optimization, dealing with uncertainty in general, in problems with application to healthcare operations, analytics, facility location problems, transportation systems, and many more. So without further ado, thank you, Karmel, for being here. And I want to give the mic and the screen to you now.
Thanks. Well, thanks for everybody for attending. Today's talk will be about our new Inexact column-and-constraint generation method. This is joint work with my brilliant PhD student, Manu, and based on our paper co-authored with my colleague, Frank Curtis. So the agenda for today, which everybody will forget, I will provide some introduction for those who don't know, the column-constraint generation, and then we'll go to our algorithm. The paper has two computational results that are based on two problems. One is operating room scheduling, and the other is on facility location. Today, I'm just going to cover one of the computational results due to time limitation. So let's get into the topic. So the basic problem setting that I'm going to be focusing on today is, most of you know, is a two-stage robust optimization problem. We have some first stage decision we make before realizing uncertainty. And then after we observe uncertainty, which is represented by this random vector Cassie, we make some second stage decision. The distributions of this Cassie is not known, but it belongs into some uncertainty set. So in two-stage robust optimization, we seek to optimize against the worst case scenario that lies within this scenario set or uncertainty set. So this is the basic setup. Basic assumptions that I'm going to make, or we made in our paper, the uncertainty set is finite or it's a polytope, which is a common assumption or standard assumption in the literature. The problem itself has a relatively complete recurse, meaning that the second stage is non-empty for any feasible first stage decision and a realization of uncertainty. The problem itself has an optimal solution. Basically, I will define the problem with finite objective value, and the implementation cost or the objective value is strictly greater than 0. And this is also common. You can see it in many applications where we actually consider implementation cost of the decision. Okay, so this problem obviously is challenging to solve in the presented formulation, simply because we want to minimize a maximum and then minimize this. So it's because of the inner maximum problem. Typically in the literature, people propose some master subproblem framework where we kind of take this problem, formulate some master problem, which is a relaxation of the original problem. We get a lower bound, then we send a feasible solution to the sub-problem, and we solve it somehow. We get some upper bound, and then we send in this new information or a new cut to the master problem. And of course, we terminate once the optimality gap between the master problem and the sub-problem reach either some pre-specified tolerance or reach 0 if you want to solve it exactly. This is not meant to be a comprehensive list of literature related to our paper, but the work that we're proposing. But I wanted to point out that in this master subproblem framework, there are two perspectives. One is the BD, which is the Van der decomposition, which is dual perspective, where we actually obtain a lower approximation of the objective value using the dual of the second stage. And then we have the primal perspective, where we obtain lower approximation of the objective value using second stage constraints and variable. The first, or the state-of-the-art common constraint generation, the first one was proposed by Zeng and Zhao, which I'm going to cover next. And then there are a couple of folks that, in addition to those who I mentioned here, that worked on dealing with the challenges of solving the sub-problem of this common constraint generation. So let me kind of like introduce how this common constraint generation works, which is the original method. So we have a master problem, which given a subset of the scenario set, we solve this master problem. We get them some decision X, and we record this delta and also X that we solve, and then we obtain a lower bound on the optimal value. Then we solve some sub-problem given a feasible solution from that we obtained from solving the master problem. And then this gives us an upper bound, and also we obtain some scenario casino. So how the algorithm work: after we solve the master problem, we solve the sub-problem for a feasible decision. After computing the upper and lower bound, we check if we reach our termination condition. If not, then we enlarge the scenario set. And by enlarging the scenario set, basically we add a scenario and the variables, second stage variables and constraints, we send them to the master problem and we repeat. Of course, once we reach the termination condition, we return the best solution found so far. Okay, so this is the standard CNCG. Of course, some assumptions has been made, such as the min-max sub-problem is solvable. So I'm not going to cover how we solve the sub-problem. We're just going to assume that it's solvable, for example, via an optimality oracle. And if the uncertainty set is a polytope, then the oracle output an extreme point of the uncertainty set. And then this is, we identify new scenario and we enlarge the uncertainty set. So the colleagues here, they actually proved that this CNCG under this assumption will terminate in a finite number of iterations. Personally, I like CNCG because I've tried it into many DRO, distribution robust optimization problem, and RO, and the computational performance for has been promising. But the challenge of applying column-and-constraint generation is that solving the master problem in many applications might be challenging, simply because it could be a large scale optimization problem, for example, mixed integer programming problem. This means that it takes a lot of time to solve the master problem in each iteration of the algorithm, which impact the overall computational performance. And this challenge is exactly what our paper aim to address. Okay, so let's get into the business. So how our algorithm work? First of all, the master problem looks somehow similar to the master problem in the original CNCG, but we have given some L bar, which is a lower bound on the objective value, and the subset of scenario. We try to solve this master problem. And as you can see here, I highlighted this because this is an additional constraint where we provide a lower bound on the optimal value of the master problem. So we kind of give a bound to push the lower bound of the master problem. Where exactness happen is, instead of solving this problem to optimality, we are going to solve it to some inexact tolerance gap. And then we're going to record the best feasible solution found once we terminate at this gap. And then we record, in addition to that, we record a lower bound and an upper bound on this optimal value of the master problem in each iteration J. And to obtain these guys, we obtain them from the solver. So once you solve it, you can actually, as you solve it, you can obtain the lower bound and upper bound on the optimal value of the master problem from the solver. Now, if this lower bound that we obtain is strictly greater than this L, then we actually record, we set L equal to J, which is the trace, the most recent iteration where this LJ provides a valid bound on the master problem. Then we update L bar to UJ that we obtained from the solver. And don't worry, you might say that this is, this introduces another layer of inexactness, but later on in the algorithm, we actually correct this inexactness using the so-called backtracking routine. Sub-problem is the same because, as I said, I mentioned earlier, the sub-problem remains the same as what we do in the original CNCG. Now, as I said, we correct inexactness. So we have the so-called backtracking routine, which balance the trade-off between the computational gain that we gain by solving the master problem inexactly and inexactness. So in this system, we compute the actual relative gap, which is U bar, the upper bound that we computed, and L, so superscript small l, and the inexact relative gap, which is computed by y bar minus yj that we obtain. And remember, we obtained this from the solver. Now, if this actual relative gap is below the termination condition, so it's similar to CNCG, we terminate, okay? But if this actual gap is below what we call backtracking routine, below this termination condition, then we go to the backtracking routine step. And in this step, we either go to exploitation or exploration. Exploration, as you can see, if this inexact relative gap is above our backtracking routine parameter, then we basically, it's similar as CNCG. We increase the scenario set. We go back to solving the master problem. In exploitation, if the inexact relative gap is below our backtracking routine parameter, then we go to exploitation, where the algorithm will try to exploit the knowledge of this lower bound by updating this L bar, and recall this L bar is here. So we update the lower bound information here. So we exploit this information. And to correct inexactness, we reduce this inexact optimality gap that we use to solve the master problem. And then we go back to step 1 again. Okay. So to kind of put things, compare with the original CNCG, so we do the same thing. We solve a master problem, but instead of solving it to optimality, we solve it to an inexact relative gap. This L, small l, is track again the most recent valid bond on the optimal value of the master problem. We solve the sub-problem as in original CNCG. If the actual gap is below a termination condition, we terminate. If not, then we go to backtracking routine. And in this backtracking routine, we compute some inexact gap. If this gap is below our backtracking routine parameter, then we go to exploration step, where we enlarge the scenario set, we add variable and constraints, and we solve the master problem. If it's below that, then we go to exploitation step, meaning that we exploit the most recent information of valid bond. We update L prime, so L bar, and then we solve the master problem. Okay, so some of the questions that come into your mind is, then what's the theoretical guarantee of this new ICNCG? Basically, because of this inexactness that we introduce. Okay. So let's get into that. So the first question is whether this L that we use provide a valid lower bound on the optimal value of the original problem. The answer is yes, because in this proposition we actually prove that by going over all of these steps, when we update or we exploit this knowledge of the lower bound from the solver, is actually provide a valid lower bound on the optimal value of the original problem. And this justify the use of this, what we call actual optimality gap, as a gap to consider for termination. The second one is we need some upper bound guarantee on the actual relative gap. So once you terminate, what would be the actual relative gap? And we find that it's bounded by, as you can see here, by the backtracking routine parameter. And the other part of this function is the inexact gap that we use to solve the master problem. So basically, this upper bound helps us to quantify the exact solve of the master problem on the actual relative gap. Okay, so using these two propositions actually, and we were able to answer the second question, is whether this algorithm converge in a finite number of iteration or not, because you don't want to be looping forever. So we found out that if you choose the backtracking routine parameter, remember this parameter is the one that did tell us whether we go to exploitation or exploration. So if it's below epsilon over 1 plus epsilon, which is, remember, this is the termination criteria, then our algorithm will terminate in a finite number of iteration. And the proof is really simple. Basically, you can imagine that if the algorithm does not terminate, then it will go to the backtracking routine. And in the backtracking routine, we either go to exploration or exploitation. But if at the exploration, every time you go to the exploration, the scenario set will be enlarged. But if your answer, the scenario set is finite, then you go to finite exploration step. So this is if you go to the exploration. Now, if you go to the exploitation, recall that every time we visit the exploitation step, we actually reduce the inexact gap, and eventually this gap will go to 0. And therefore, we will go to finite exploitation steps. So this kind of shows that this ICNCG will also terminate in a finite number of iteration. Okay. Sorry, I speak so fast. So if somebody wants to stop me and ask me a question, you can. Otherwise, I'll just continue like a train. Okay.
I have a question. Here, your L bar that you are using, it's arbitrary, right?
No, it's not arbitrary. Actually, we update it every time we visit the exploitation step.
No, I mean the starting value of L bar that the L under, like at the start of the algorithm, you choose it arbitrarily, right?
You can choose it here 0 to start with, and then once you do the first solve, then you can update it.
Okay. Okay. Thanks.
You're welcome. Okay, so the next question. So we show we have some theoretical guarantee. We prove that it converges in finite number of iterations. The next question is how to choose the parameters that are involved in this CNCG algorithm. The first one is the most important guy here, which is the backtracking routine parameter, which tells us whether we go to the exploitation or exploration. We found that if we choose this parameter close to its upper bound, then the algorithm will always favor exploitation, where we exploit the most recent knowledge of the valid lower bound on the optimal value. In terms of choosing this value, which is the inexact gap that we solve the master problem to it, and alpha, which is the one that we use to reduce this gap each time we visit the exploitation, we found that if you start with this inexact gap large, then a small alpha will help you to shrink it at a faster rate, so you kind of correct inexactness faster. But if you choose this inexact gap comparable with the termination gap in the optimality condition, then a value of alpha closer to 1 will shrink it slowly. And lastly, to show that this algorithm is indeed a generalization of the original CNCG, if you set this inexact gap to 0, and then you choose the backtracking routine to be less than the termination threshold here, then basically every time LJ and UJ will be, the master problem will be solved to optimality. So the upper bound and lower bound you obtain from the solver at each iteration equal to each other. And also this L bar is indeed a valid lower bound, and therefore you update this small L here every time to the iteration of CNCG, and the backtracking routine reduced to nothing more than checking optimality. So this should convince you that indeed this CNCG, by being smart in choosing the parameter, you can actually, it's a generalization of the original CNCG method. Okay. All right, and the last theoretical part is we also consider some variant of our CNCG, which show its flexibility. The first variant is allow us to control the number of times or to go or enforce the algorithm to go to exploitation step. Basically, sometimes what it could happen as you solve, you might skip the exploitation and go to exploration step again and again and again. So this allows you to, this variation allows you to set some exploitation frequency, which basically tells you go to the exploitation step after after skipping it for F exploit time. And this helps you to remedy situation when the valid lower bound information is not exploited for a long time. The second variant, although we actually introduce inexactness to solving the master problem, sometimes it's a really, really difficult problem that you cannot solve within maybe an hour or 2 or 3. So this variant allows you to set a time limit for solving the master problem. And if you wonder, this is, yes, another source of inexactness. But to correct this source of inexactness, every time you visit the exploitation, in addition to reduce the gap, you are going to increase this time limit, which will help you to reduce inaccuracy. The main advantage, as I said, this will help you at the beginning, at the start of the algorithm, when the lower bound is very low, it helps you to skip from challenging master problem at the initial iteration. Okay. Okay, so this is all the theoretical part of my talk today. I know we all like to see then how this algorithm performed computationally. In the paper, we actually tested using 2 different problems. One is distribution robust operating room scheduling problem, and the other one is robust facility location problem, which I will skip today, but you can check that in the paper. So what is this operating room problem? It's a basic setting. We want to decide which OR to open and assign each surgery to open OR. And those who work on healthcare scheduling, they know that although we have these 2 decisions, but this problem is one of the challenging problems because of these 2 binary variable. I'm going to consider a set of elective surgeries that we want to schedule and a set of ORs that we need to decide from which OR to open. I'm going to use D as a random surgery duration, and we will assume that this D has a known lower band and upper band, which in healthcare makes sense because a surgery cannot be below negative. So you can set this lower band to 0, and then upper band, clinically speaking, you cannot go forever performing a surgery. We're going to set the length of the working day or the OR opening hours to T. Beyond this T, we're going to incur a cost of overtime. The cost of opening an OR is CF, and the cost per unit overtime cost is, I'm going to call it CV. This problem has, again, two decision variables. The first binary decision variable will equal to 1 if we open an OR, and YIR equal to 1 if surgery I is assigned to this open OR and otherwise not. So this is the formulation of the problem. Let me first talk about the constraints, and then we'll cover the objective function. So this is basically says you cannot assign a surgery if the OR is not open. So once you open it, then you can assign a surgery to it. And of course, a surgery cannot be assigned to multiple OR. So this constraint says assign a surgery to one OR only, and this is binary restriction. In terms of the objective function, we want to minimize the fixed cost of opening OR. And this is a DRO problem where we minimize the expected cost of overtime. Since the distribution of surgery duration is not known, then we consider a DRO counterpart of the problem where we seek to minimize the maximum or the worst cost expectation of the overtime cost. As an example of the ambiguity set here, so we assume the distribution belongs to an ambiguity set. We will consider the MAD ambiguity set, where we assume that we know the mean surgery duration for each surgery, and we also have some upper bound on the mean absolute deviation. Okay, so to generate the instances, there is an excellent set of open available surgery data, where it has 3 years of surgery data for 6 surgery type. In order to generate a sample, we sample 500 data points from this data. We set mu, which is the mean of surgery duration, and the upper bound on the MAD as a sample mean and the absolute deviation. And these upper and lower bound, we consider 2 setup. We take the 20th and 80th quantile of the sample data, or the 10th and 19th quantile as an approximation of these upper and lower band. We tried different parameter set. So this is, remember, the set of surgeries that we are going to schedule from 20 to 25. And as a set of OR, we tried from 7, 8, 9, and 10. In order to generate the number of surgeries per type, we just use a multinomial distribution. And as length of the day, we considered 480 hours, which is a standard in this literature. And as a cost parameter, remember, this is the fixed cost, and this is the overtime cost per unit overtime cost. We consider these two setup. Now, for ICNCG parameter, as an initial inexact gap, we considered actually a low gap, which is 2%. As a time limit, remember the variant of ICNCG, we consider the 300 seconds. So after it's, this means that the algorithm will terminate, the master problem solving it will terminate under 2 conditions. Either you reach this 2% or you reach this 300 second. And as a backtracking routine parameter, we consider 1.5%. To reduce the inexactness in each exploitation step, we consider 0.8. So every time you reach the exploitation step, you reduce this MD like this, okay? And in addition to that, we increase the time limit. So tau each time will be tau plus 800 seconds, okay? So let's look at the results. So what you see here is basically the time performance profile of both the CNCG and ICNCG. For ICNCG is everything that's marked in blue, and for the original CNCG is everything that is marked the lines in orange. So the curve represents the percentage of instances solved by each of these algorithms. The solid lines is basically we solved it with termination condition 5%, and the dotted line we solve it with a termination condition 2%. Clearly, as you can see, our ICNCG can solve a higher percentage, significantly larger number of instances than the original CNCG. And in addition to that, it's actually solved the instances in significantly lower solution time. This is both when we use an upper and lower bound to be a 20th and 80th quantile. So this is under the first cost setup. Similarly, under the second cost parameter setup, you can see that ICNCG solves significantly a larger number of instances, and indeed this CNCG struggled to solve many instances that we generate for solving this problem. If you consider the setting this lower bound and upper bound to be the 10th percentile and 19th percentile, so meaning that you make the ambiguity set even larger or bigger, then you can see that actually CNCG cannot solve most of the instances within the time limit, which is 2 hours, but ICNCG can solve all of the most of the instances, approximately here, for example, 80% of the instances. Okay. So the next question you might ask then, for those instances that the both algorithm can't solve within the time limit, which is 2 hours, what is the optimality gap? So this is the performance profile that presenting the percentage of instances. This shows the proportion of instances solved at a final relative gap of 2%. You can see that our ICNCG only can solve larger instances within the time limit. And for most instances, the final that they cannot solve within 2 hours, the relative gap is 10%. So as you can see, if you go down here, for those instances not solved in the time limits, the relative gap at termination is just 10%. In contrast, if you look at the original CNCG, most of the instances actually terminated with a large optimality gap. And this is both if you use 20th and 80th quantiles and 10th and 19th quantile. So this shows you that even if the two algorithms cannot solve instances within some time limit, ICNCG terminate with a very lower gap, so with solutions that are close to optimal solution. This is again under the same curve as you've seen, but now we changed the cost. Again, the ICNCG can solve most instances when it terminate with optimality gap that's very low, that's near 10% and below, but the original CNCG terminate with a very large gap as compared to our ICNCG. Okay. So this is basically the computational results that I want to discuss today. And to conclude and open for a question, just to summarize some key contribution, we proposed a new inexact column-and-constraint generation method. The main purpose of this algorithm is to address the computational issue that's associated with the master problem. We also present a variant of this algorithm. So you either solve the master problem to inexact tolerance, you can also increase the exploitation frequency, and you can also increase the time limit or decrease the time limit depending on how your master problem, how much it's challenging. We equip this ICNCG with a backtracking routine, which help us to manage the trade-off between inexactness and computational gain provided by this inexactness. We show that our ICNCG can converge in a finite number of iteration, and using two different real-world problems such as scheduling problem and a facility location problem, we show that our ICNCG outperformed the state-of-the-art CNCG. Okay, and with that, I'm going to see if anybody has a question, but first let me thank you for listening to my talk. And by the way, this is the references that you've seen today.